welcome to this fourth video in the unit on chemistry for Year 7. This lesson is about chemical reactions, and it's building on the work we've done so far about atoms and elements and compounds. In the last lesson we looked at molecules, and it's firstly reinforcing the first of our big ideas in this chemistry unit, which is this idea that elements are made up of different types of atom, and an element is all made up of the same type of atom, but that is the fundamental unit of matter, at least for the time being. And we're going to introduce the second big idea here, which is conservation of mass. And we're not going to go into loads and loads of detail about conservation of mass. This is something that's going to be implicit in Year 7. We're going to make it explicit in Year 8 when we look at phlogiston and things like that. But I think the way we draw our diagrams, starting in particular in this lesson, is going to be really helpful at reinforcing this core idea about conservation of mass. So the first part of the lesson is actually a bit simpler. It's just making sure students are clear on some of the formalism of how to write chemical reactions. So I quite often like to start with making a pancake. You might have a different example that you use, and that's fine. But I give them the idea that when we're making a pancake, we start off with our ingredients, and we call them ingredients like this. So what are the ingredients of a pancake? Well, I'm just going to say, let's keep it simple. So we've got flour plus milk plus eggs. You may put more in, but that'll do for now. These are the ingredients. And what we need students to understand, we'll look at chemical and physical changes later in more detail, but what we really need them to understand is that when we mix all of these together and then we apply heat, something very special happens. Actually, we get something that's qualitatively different. In this case, a pancake. And you could call that the meal or whatever, something like that, just if you wanted to categorize it. Now, what I like to draw students' attention to, and actually maybe I should have done this in a different color, when we think about this, we don't need to be chemists. We don't need to be scientists to think about what happens. This is a way of writing it, but I think that's something that students will already be fairly familiar with. That if you start with 3 ingredients and then you do stuff with it, you end up with a meal, in this case the pancake. What we need to draw their attention to is that this is an everyday way of thinking about it. This is the way you would think about it if you were just an ordinary person making pancakes in your kitchen. You would think about it in terms of the ingredients you start with, the meal you end up with. But what we want to do is think about it in chemical terms, or maybe more broadly scientific terms, but I'm going to say chemical. And what's important is that if we're chemists and we're thinking about this, we're looking at the same thing, but we're looking at it in a different way. So in this case, as chemists, we don't call the things that we begin with the ingredients. As I'm sure you know, we call them the reactants. And the pancake, we don't call the meal as chemists. We say the pancake is the product. And the final thing to emphasize is that what this arrow is representing, later on we'll talk about it as energy transfer and you know, when we get to activation energy and endothermic, all of that sort of stuff. But for now, we're just going to keep it really simple and say what that arrow represents when we're thinking about something like making pancakes as chemists. What that arrow represents is a chemical reaction. And the first part of the lesson is just practicing identifying reactants and products from various chemical word equations. That, I hope, should be pretty straightforward. Now, the second part of the lesson is a little bit trickier, but really not introducing too many new ideas. It's just applying it to real-life examples. And the demo that's in the slides, and I think it's a great one because, as I'm sure you all know, burning magnesium, that's the example in the slides. It's a great one because students just love seeing bright white lights and it's all very exciting. But what we've got to make sure of is that students are attending to the right things. And in this case, what we really care about is the idea that the reactant that we started with, certainly the visible reactant, which is magnesium, is very different to the product that we end up with. And that's what you really want to emphasize to your students. So they're not just like, oh, that was cool, I saw a bright white light. So that they're actually thinking in terms of the concepts that we want them to think about. So whenever I'm doing chemistry, I tend to lay it out like this. Start with some sort of diagram, if possible, of the concrete laboratory experimental setup. So in this case, we might have our ribbon of magnesium. Maybe I'll draw something like this. That's our magnesium. You might want to label that. I might just call it Mg for the time being. If you wish, you can write it out in full. That's fine. And we want to show them what happens when we apply heat. So I might do this using Bunsen burner. So I'm going to apply heat like that. In fact, let's make a better drawing here. So I'm going to draw my Bunsen burner and apply a flame like that. And again, it's quite tricky in this sense, and this is the classic example, isn't it, of illustrating conservation of mass. We don't want to go into that in too much detail right now. So for the time being, you can just tell them that what's happening here, if we were to zoom in on a micro level, what's happening is the following. That actually, if this is our magnesium ribbon with lots and lots of magnesium atoms, again, we can keep it with, we don't need to go into metallic bonding here or any of that. We can keep it fairly simple, kind of solid, liquid, gas, particle diagram type situation. So if we just draw some magnesium atoms like this, what we want to say to students is, well, there are oxygen atoms out there in the atmosphere that are going to somehow react with the magnesium atoms in here. And I'm going to show one of these coming in like this. Now, of course, the more eagle-eyed among you, and probably the more eagle-eyed among your students, are going to say, well, hang on, last lesson you said oxygen is this diatomic molecule. It exists as O2. Why these single O's? It's a good point. And actually, as with all these things, it's a bit more complicated than we make out. The reason I do it like this is because it's a nice example that's easy for teachers to demo, and we can use it to illustrate the point, which is, again, what we're focusing on here is just the fact that something new is formed. That is the fundamental point about a chemical reaction I want to get across at this stage. But I also want to show that with the big idea that actually mass is conserved. So for the time being, I'm just going to treat oxygen as a single atom, just to keep the story simple. And then what I want to do is show students that, okay, if this was the case, that these oxygens, maybe I could do a few more, these oxygens are going to come and join to the magnesiums like this. Maybe that one could go there. And what we're going to end up with after this has happened is something new. Instead of having all those Mgs and all those Os as separate, we've now got Mgs and Os chemically bonded together. So I'm going to put Mg and O, Mg and O, Mg, O, like that. And if I just move that like this, what I like about these diagrams is that we can operate at different levels. So this is the kind of macro level. This is what they can actually see. This is a picture that kind of explains what's going to happen. And then the final thing we can do is do that at an even more abstract level, which is to say, well, let's do an equation for it. Now, what I quite like to do here, I might say, okay, what's happening here, what's happening in this reaction is that we've got magnesium plus oxygen. What do we have here if we've got magnesium and oxygen bonded together? We're going to look at this in more detail next time. For now, you can just tell them. We get a compound called magnesium oxide. I think it's fine just to tell them. But the really important point, and I think teachers often forget to do this, is once we've done this and we've given them this abstract thing, we've got to go back to the concrete. And I like to do it in a kind of U shape like that, although I have drawn these at the top here. But I like to go from macro to micro to abstract symbolism. But then we've always got to go back to the macro, back to the concrete again. And in this case, what we saw wherever you have your wherever you did your reaction, but you'll have that kind of white powdery stuff, and that is your magnesium oxide. I'll write it out in full this time. Oxide. And what you want to draw your students' attention to is the fact that something has changed. There's clearly been a change in what's happened. In what exists in the material that's there, and that change is what we're referring to when we talk about a chemical reaction. Now, there's other examples like this, and for each one, I would draw diagrams kind of similar to this. You may not always wish to do the macro diagrams if you think it's unnecessary, although I think it is useful to separate out those different levels, but show what's happening at the macro level, certainly show what's happening at the particle level, and then use that so that students have an idea of how we would represent that in a chemical word equation. And always, once you've done that, don't forget to then go back to the concrete to show what are the products going to look like at a concrete level, and that's what's going to really help them get a sense of what these chemical equations are trying to represent. So what you'll see is there's lots and lots of examples in the slides. So I think the next one is hydrochloric acid and sodium hydroxide. And again, you could demo that in the lab and show them what's happening, maybe show them the indicator, show that something is clearly changing. And if you then represent that using the particle diagrams and then make it even more abstract in terms of the word equation, that's giving students a really good sense of what it is that these chemical equations are there for. I hope that's all clear. In the next lesson, we'll look at this stuff a bit more. We'll be naming compounds.